So now we're ready to get into variation of parameters. Remember, this variation of parameters, the purpose of this is to solve a non-homogeneous second-order equation when the forcing function is not simply an exponential, a sine or cosine, or a polynomial, or a combination of those. So other types of functions. We'll do an example a little bit later with the secant function, and you'll see others on your homework. But anything other than the three types that we talked about with undetermined coefficients, we'll need to use variation of parameters. So it's a more general method. The theory behind it is a little bit more complicated, so we'll spend a fair amount of time talking about the theory behind it, but when it comes to actual problems, basically boils down to a couple of formulas that you can use. So we'll spend some time developing these formulas, and that's what most of the videos are going to be for this section. Before we get into variation of parameters, I have to develop one thing first, and this is what's called the Wronskian. This is named for a Polish mathematician named Wronski, but the Wronskian is a determinant of a matrix, and we'll talk about what that is in a second. But before we get into variation of parameters too far, we'll run into a situation where a determinant of a matrix will make our formula much simpler, and so we'll want to take advantage of that. So this will develop this Wronskian, and then it'll have to kind of sit on a shelf for a little while until we get back to the point in the variation of parameters method where it becomes useful. So kind of have to stick with me for a minute here. We'll just develop it kind of in isolation, and then it'll become useful a little bit down the road. So for now, just think of it kind of on its own as just a determinant of a matrix. So this W is going to be a determinant of a specific 2x2 matrix. Now, if you've taken Calc 3, for instance, or linear algebra, or a similar course, you have some familiarity with matrices and determinants. We're not going to go too far into this. We're kind of just going to get the bare minimum information that we need. And then as you have time later on, you can learn in other classes. But we're just sort of getting the bare minimum. So what happens is we take a matrix, and this matrix has two functions. Call them F1 and F2. All right, so we have F1 and F2, these two functions. And then we set up this matrix. So this matrix where we have F1 and F2 on the first row. And then on the second row, we put their derivatives. Now again, we don't know yet why this is going to be useful, but bear with me. A little bit later, we'll have a situation where this becomes useful. Then if you take the determinant of this, so that's what these vertical bars are doing, you get the Wronskian. You get a value for this W, Wronskian. Now, if you haven't seen a determinant before, for a 2x2 matrix, the determinant is calculated this way. You multiply along each of the diagonals. So you multiply along the first diagonal here, and then you multiply along the second diagonal. And then you take the difference between those two. So the value of this determinant would be F1 times F2 prime minus F1 prime times F2. So there's number one, there's number two. So on the formula sheet for this upcoming test and later ones, when you need to use variation of parameters, this will be given to you. So this formulation, so you can see it written this way. What you need to remember is how to take this determinant. So you multiply along the one diagonal and then the other, and you subtract in this order. So that's the part you need to remember how to do to find this determinant. So let's say, for example, just a few quick examples of what the Wronskian would look like. Let's say our first function was t squared, and the second function was 3t squared. This is an example. The Wronskian would be set up this way. So you have f1 and f2, and then their derivatives. So the derivative of f1 would be 2t, the derivative of f2 would be 6t. And then to take the determinant, you multiply along this first diagonal. So t squared times 6t, that's 6t cubed. And then multiplying along the second diagonal, 3t squared times 2t, that's also 6t cubed. So notice that when you subtract these, you get 0. Now this is one interesting property about the Wronskian, that we've noticed this idea before. If you look closely at these two functions, we've talked before about functions being linearly independent or not. And it should be clear to you that these two functions are not linearly independent, because if you take f1 and multiply it by 3, you get f2. So one of them is a constant multiple of the other, or each of them is a constant multiple of the other, right? So this is one use of the Wronskian. If the Wronskian comes out to be 0, then it turns out that it's likely that that means that these are linearly dependent. And without going into too much detail, without saying anything more, it doesn't completely guarantee it, but for anything that we'll see, we shouldn't see any examples where the Wronskian being 0 does not mean it's linearly dependent. However, on the other hand, if the Wronskian is not 0, we can be certain that they are linearly independent. Let me show you an example. So say, for example, we have something like e to the t and t e to the t. So here are two functions. If we set this up again, now these, by the way, you should notice are linearly independent. Those are the example that we've used with the homogeneous case with one root. So here's f1, here's f2, and then f1 prime would also be e to the t. f2 prime, if you use the product rule, you would get something like this after some simplification, right? And then when you go to take the determinant of this, you'd multiply along this first diagonal. So you'd have 1 plus t times e to the 2t, right? E to the t times e to the t is e to the 2t. And then you'd multiply along this diagonal. So again, you'd have t times e to the 2t. Now notice when you do this, that some of this part cancels. So this t and e to the 2t cancels with all this, but it leaves behind a 1 times e to the 2t. So this comes out to something other than 0. And that does indicate that these are linearly independent. So that's one use of the Wronskian, is to verify that two things are linearly independent. If you take the Wronskian and get something non-zero, then that means the two functions are linearly independent. If you get 0, it means that they are probably linearly dependent. So there could be a case where you can come up with some functions that don't fit this, but at least the first side is a strong conclusion. If you get something non-zero, they are for certain linearly independent. So there's some more theory behind this that we won't get into, but for now, the Wronskian, you should know how to calculate it. Set it this way, so it's a determinant specifically defined for two functions. And we have some sense of one use of it, but other than that, we'll have to wait to find out why this is important for the variation of parameters method. So we'll set this aside for a minute and talk about some more background, and it'll turn out that a formula comes out in the variation of parameters setup, and in that formula we'll have something that looks like this, which will be much easier to just call that W to make our formula simpler. That's kind of the idea of why we're using this.